Thank you, Alfonso. And thanks to the organizers, Holger, Massimo, and the rest, because I'm pretty sure organizing something across multiple time zones and multiple modalities has been extremely fun. So we appreciate it. Anyway, so today I wanted to talk about basically quantizing neural networks. And this is joint work with my former PhD student, Eric Leibrand, current PhD student, Jinji Jiang, and very talented undergraduate, Yixuan Zhou, who has been responsible for running most of the numerical experiments on some large neural networks. So large for me, at least. So these are some links to papers and code. If anyone is interested, I'll be happy to share afterwards also. Okay, so the motivating question here is essentially due to the size of these neural networks. So in particular, we see on this slide that we have these neural nets for doing image classification. They tend to have parameters, 480 million parameters, 830 million parameters, and they do pretty decent jobs in terms of the accuracy of the task, something like 90%. But squeezing this extra performance out is now becoming a game where the complexity is just almost out of hand. And and this is just image processing. When you hit natural language processing, it gets nastier and nastier. GPT-3 is something like 175 billion parameters, and there are others with something like 530 billion parameters. So these neural nets are getting quite large and unwieldy, and squeezing even a little bit more out is requiring even more parameters. So there's the question of, does the whole model require rethinking? But that's not really what I want to discuss. Rather, what I want to discuss is the question of, okay, we have all of these parameters. Is there any way that we can simplify a little? So you could simplify by trying to compress layers. You could simplify by trying to quantize weights, for example, by changing them to ones and zeros and negative ones. The 0 ones are great because you get rid of a bunch of connections, and the ones and the negative ones are nice because doing calculations with addition and subtraction is much nicer than doing calculations with floating point numbers. So the point is that if you are able to do something like this, you're able to miniaturize, reduce power complexity, reduce storage complexity, and obviously what you'd like is to keep the performance the same or as similar as possible. And I should say, you would like to do it in a reasonable amount of time. So because you have something like hundreds of millions of parameters, you don't want your algorithm to be polynomial time complexity in the number of parameters with some large exponent, because you wouldn't be able to quantize your network in any reasonable amount of time. So here's the setup. Say you have some function phi, that's your L-layer neural network, and it's the usual thing, alternating linear and nonlinear layers. The nonlinearities are component-wise nonlinearities, so things like the ReLU function. And I call them linear, but they could be affine, and this is the usual representation of what a neural network looks like. So the only thing to keep in mind is that these weight matrices are capital W. I'm going to ignore biases in general because we could always embed into a larger, into a one-dimension larger space and just work with linear objects. So what is our goal? Our goal is to take the model from the previous slide where we have linearities and non-linearities alternating, each linearity identified as WL, and I want to replace all these matrices WL by new matrices QL, where the QLs are plus minus ones and zeros. So the approach that we're going to follow is a little bit different than some of the approaches that were present in the engineering literature up to a few years ago, where they basically tried to learn the neural network as a quantized neural network from the beginning. So they tried to write some optimization function and manipulate the optimization so that they can try to solve this integer programming problem, ad hoc approaches, and hope for the best, then try it out, and turns out that it works. What we'll do is something different. We're gonna assume that we have our already trained neural network with the weights handed to us, and we'll try to take that neural network and replace it with a quantized counterpart. So for that, we're going to need data. For this talk, the data will be organized as rows. So each data point is in n dimensions, and I have m data points. I have my already trained neural network, as we discussed, and somebody hands me an alphabet that they would like me to quantize to. Could be -101, but it could be more than that. It could be 4 bits or 5 bits or whatever is appropriate for the task. And the goal, for the purposes of doing analysis, is to reduce the Frobenius norm error. So you're going to take all your data points, feed them to your unquantized network, all the data points, feed them to your quantized network, and you would like the difference in output to be as small as possible. And here I'm sticking a for every L, because I would like that the output to be as similar to the output of the quantized network to be as similar to the unquantized network at every layer. But that's more of an algorithmic question. Ideally, you just really care about the final output. So let's focus on the first layer for the purposes of the mathematical analysis, and then we'll generalize the algorithm to more layers, and we'll show that things still work out, even though the mathematical theory is for one layer. So really, the basic observation that makes this approach work is a very simple one. So you have your quantized weights acting on your data. And so you can write them in matrix notation. This is your data, these are your quantized weights, these are your unquantized weights. This is a Frobenius norm. So basically, you can write your matrix, you can notice your columns, and then you're basically summing over all the columns, the L2 norm squared. So in other words, minimizing this Frobenius norm is equivalent to minimizing each one of these summands. And each summand corresponds to a single neuron in your layer. So each one of these guys is a vector. Okay, so this is a reduction. It allows me to basically focus on only one of these things. And because I can only focus on one of these things, I can drop my superscripts now and just say W is a vector, Q is a vector. That basically means that what I would like to solve is this optimization problem. I would like to find a Q sharp that minimizes this L2 difference. Now, suppose that you could solve this problem. First of all, there's no guarantee that this can be solved in the sense of finding the global minimum in a reasonable amount of time, because this is an integer programming problem. In general, it's not easy. And the second question is, even if you could do it, are you guaranteed to get a small number? So we'll show that with our algorithm under certain conditions on X, we'll be able to get this to be small. And we'll also come up with an algorithm that will not minimize this thing, but will find us a good enough approximate solution. So this is the game we'll play. The approach, as the title suggests, is greedy. So what we'll do is we'll notice that the matrix vector product is again a sum of things. So it's a sum of weighted columns of the data matrix X minus weighted columns again, but this time with the quantized weights. This suggests that you could devise an iterative algorithm where you look at the sum up to step t rather than all the way through to the dimension. And at each step, you try to make a decision about which Q to choose from your alphabet so that the two sums track each other as closely as possible. So completely greedy. Then you can write down your algorithm. You initialize some error vector U0 to 0. And then at each step, you pick the element in your alphabet that minimizes the sum of the error you're going to make in this step plus the error you've been accumulating so far. And then you update your error, old error plus new error. It's a very simple algorithm. And at first glance, you might think that this might be potentially problematic because you have to pick an element from your alphabet, but it turns out that it's pretty straightforward. All you have to do is do a scalar quantization of the weight, which is a scalar right now because the teeth weight, plus an inner product between the column of your data matrix, your previous error vector, and appropriately normalized. So this is just scalar quantization and easily computable. So if your alphabet is nice and well-behaved with equi-spaced things, this is just a rounding operator right here. And yeah, nothing computationally expensive in any of these steps. So if you wanted to count flops, you would notice that you're running your algorithm for n steps. Each step requires an inner product of m-dimensional objects, so that's about m operations, and addition is also pretty cheap, so ultimately you're doing mn operations total. The size of your data matrix was mn to begin with, so this is of computational complexity that's comparable to just running over your data once. In fact, running over your data a constant number of times. So there's no polynomial scaling in dimensions, which is nice because if you want to deal with these large neural nets, you can't afford to have polynomial scaling. Okay, so this is the algorithm. This is a theorem, and we'll run through it. It's not overly complicated. So let's start with a distribution of data. Of our data. So this is a distribution on the columns and of X. And we're going to suppose that the distribution satisfies this inequality. So draw vectors from the distribution. You would like the expected square cosine of the angle between your vector and an arbitrary vector u to be bounded away from 0 by s squared. So this is inner product squared divided by norm. So it's a cosine squared theta, and theta is the angle between your random vector and an arbitrary vector u. You would like it to be bounded away from 0 for any vector in your space. So this is the first condition, and then the second condition is relaxable, in fact, but for the purposes of this theorem, it's let's keep it. You want your data not to blow up, so you want it to be bounded by something. And if those two conditions hold, and you have some alphabet where the elements are separated by step delta at most, and if your weights are also bounded, so you don't have, if your alphabet is -1, 0, and 1, then your weights can't be too large. And you go and you run the algorithm, what you can guarantee is that the error is small, where small depends on the size of the columns of X, so that's our R. This makes total sense, it's just a scaling parameter. In the denominator, this cosine squared shows up, and then there's a very mild dependence on the number of, on N, and finally, this holds with high probability in N. So this is the kind of result that you want. Now the question is, can we go and find some distributions that are interesting and see what a theorem like this gives us in those cases? So the good news is that this is not once you have the theorem, it's not a hard exercise. So you could start with independent Gaussians because that's what we always start with. And if you do that, then you'll see that the theorem gets you the norm squared of the error being bounded by m log n. So this is interesting because X is an m by n matrix and W is a vector of size n. So you're getting a control of this quantity with very mild dependence on n. You could relax Gaussianity, replace it with Bernoulli. You could replace Gaussians with Gaussian mixture models, which might be interesting for quantizing later layers of a neural network where the neural network, let's say it's doing classification task and it starts to cluster things around so that, at the final layer, it can say this is the cluster of cats and this is the cluster of dogs. So basically this tells you that Gaussian mixture models are okay. And the theorem also holds for convolutional neural nets, where the weights have a very specific structure, but still assuming random x's. So these are just corollaries of the theorem from the previous slide. This is one example of those corollaries. This is just a reformulation of what I wrote. I'm dropping the square here, so now I get a square root. And the reason I'm bringing this up is because I want to compare it to the Komlosh conjecture. So the Komlosh conjecture is essentially a very similar problem, except that XW is 0 in that case. So somebody hands you a collection of vectors in the unit ball, and basically asks you to find vectors, to find scalars, -1 and 1. In the original formulation, there's no 0, such that the infinity norm of XQ is small. And the conjecture is that that this is a constant and it's universal, and there's been work on that, but we don't have the constant last I checked. And the point being that getting a constant in Komlosh gets you a C root M in general if you go from infinity norm to 2 norm. And what we have here is a logarithmic factor extra on top of that. So this suggests that it's going to be difficult to improve on this much further. Okay. What about relative errors? Because they're scaling everywhere. So it's important to understand how the error scales as a function of the input norm. So this is basically just saying that the scaling is going, in the case of Gaussians, it's pretty easy to see because the norm of XW is going to be pretty similar to the norm of W. And the norm of W, if W is generic, is going to be something like the square root n, because W is an n-dimensional vector. And so in those generic cases, this relative error scales like the square root of m over n, which tells you that if you have more and more parameters, the error goes down more and more, which is not surprising because you have more opportunities to cancel errors. But at least you're able to write down an algorithm that does that. Okay, a couple more corollaries that come out of the proof. If instead of having m data points that were arbitrary in space, you instead had them come from a d-dimensional subspace, then you could replace the dependence on m with a dependence on the dimension of the subspace, and that's nice because then it's not the data size that matters, but rather the dimension of the subspace that it comes from. Okay, so that was some theory describing the performance of the algorithm. There's more than this in the paper, but I thought this would be a good sample to give in today's talk. So let me show some numerics. And before I do that, let me point out the modification that one needs to make in order to deal with more than one layer. So one quick observation that you'll notice if you stare at this for a few seconds is that in the first layer, you've got the luxury of having WX and QX. So you can try to match this thing to this thing. In future layers, you already have a quantized Q. So you're stuck with a Y tilde, and here you're stuck with a Y. So now you're trying to find Q so that QY tilde matches WY, as opposed to QX matching WX. Now there's the vectors are not aligned anymore. So that introduces an extra wrinkle. Fortunately, I mean, algorithmically, that's not a big deal. You just run the same algorithm, but now instead of chasing two partial sums with identical vectors, you have two partial sums with differing vectors, and it poses no problem for the algorithm. It poses problems for the analysis. So in that case, you modify the algorithm. So now you pick your Q to minimize the running sum, as we just mentioned, with a Y and a Y tilde rather than two identical things. And then you run it on these big neural networks. Now you know how to quantize the first layer, you know how to quantize the second layer, the third layer, fourth layer, etc. They all you do them very similarly to the second one. So So now you're able to run this on some of the neural networks that have millions of parameters. AlexNet is not by any stretch of the imagination close to some of the biggest ones that are out there. But we tried it on it and on an ImageNet classification task. So what you see is two sets of figures. The one on the bottom is getting you top one accuracy. So you're looking at the output of your neural network, and you're trying to see, did the neural network classify the cat correctly as a cat? If so, that's your top one accuracy. And the top five accuracy is you look at the five highest probabilities that the neural network spits out, and you ask the question, is cat among those five? And so obviously top five accuracy is always going to be higher than top one accuracy. So this is what these two sets of figures show. On the x-axis, what we have is the size of the training data. And notice, these are very small training data sets. So you're looking at 2 to the 11, that's a couple of thousand images that we're feeding into our quantization. And then we're testing on completely new data from ImageNet, and we're getting really close to the original accuracy. So what is the original accuracy? They're the horizontal lines. And then the quantized ones are getting better and better as you have more and more training data. We ran out of being more theoretical than applied and dealing with large parallel systems and so on and so forth. We weren't really able to push this much further. I think the trend suggests that as you increase the size of your training data, you're going to get closer and closer to the unquantized networks, but we're not able to run them. The other thing to observe is that, and this is also not going to be surprising, as you use more and more bits in your quantization, you get closer and closer to the ground truth. So this is AlexNet with 60 million parameters. This is GoogleNet, which has 7 million parameters, and we see a very similar trend here. So again, you get pretty close to the accuracy that the original network has. With VGG16, now you're starting to talk about really big things, 130 million parameters, and you also get pretty close. I think the trend is pretty clear, so I won't show you all of them. This one is designed to be an efficient network. So it's designed to have very small number of parameters. This gives you less room to play with those parameters and change them, because now they're essentially all needed. There's not a lot of over-parameterization, but still, it's not so terrible. And finally, I'll just leave you with a few open questions and interesting problems, because this is a fun problem. So it's interesting to modify the algorithm and modify the proofs to account for multi-layer quantization. We're working on this, and we've made pretty good progress, but it's required some changes to the algorithm that in practice make the algorithm work worse, but it makes the theory easier to deal with. So I would like to see if we can do something with the algorithm as it currently is. We'd also like to weaken some of the randomness assumptions on the training data in terms of what we demand of the distributions. We would like to get generalization bounds. We'd like to modify our algorithm to account for some of the things that people do in practice. So in practice, when they deal with problems of this type, they'll often they'll do something, then they'll retrain the whole network, then they'll do something, then they'll retrain the whole network. And that introduces some messiness when you're trying to deal with the theory, but it really improves the performance quite a bit. And finally, a couple of other things. You would like algorithmic variations of this idea that I presented in order to deal with cases where you can get rid of layers and actually reduce the size of the network, not just quantize it. So you want to compress the network rather than just replace its weights with plus ones and minus ones. And you can do that also by introducing some sparsity promoting regularizers, and maybe modifications to the cost functions. And we're working on that. And I will stop there. So thank you for listening.